Hey everyone, welcome to The Explainer. Today, we're taking a seriously fascinating journey into how we actually use satellite data to understand our planet. I mean, we've got satellites orbiting right now, capturing absolutely massive amounts of data about the Earth's surface. But here's the thing, raw data isn't a map. To actually figure out what's down there, the forests, the sprawling cities, the oceans, we need classification. And today we're zeroing in on one of the most powerful and frankly most misunderstood techniques in all of remote sensing.
Okay, let's dive into this. Imagine you're a remote sensing analyst, right? And you've just been handed this massive consulting project. You need to map land cover across 50,000 square kilometers in Southeast Asia. Your client wants to know exactly where the forests, rice paddies, urban areas, and water are located. But here's the catch. You have just 2 weeks. You have absolutely zero field data, no ground truth, and literally nothing but a single Sentinel-2 satellite mosaic. So how do you even begin to map an area that insanely massive when you have no idea what it actually looks like on the ground?
Well, that brings us to Section 1, Unsupervised Classification Explained, or How Machines Actually See the World.
When you're staring down an enormous, totally unknown area and a ticking clock, you turn to automation, period. And that is where unsupervised classification comes in. By definition, this is an automated image classification method where the software groups pixels into categories based purely on their spectral similarities and statistical features. There's no prior knowledge required, no signature files, and absolutely no user-provided training data. You aren't giving the algorithm examples to teach it what a tree looks like. Instead, you're just letting the machine use its own mathematical logic to organize the image purely by how light reflects off the surface. It sees the world entirely in numbers and spectral bands, completely detached from our human categories.
Now, what's really interesting about this whole process is how incredibly straightforward the workflow is. You start with the raw image on one end, and it feeds straight into the clustering phase. The machine is doing all the heavy lifting here. It's only after the clusters are fully formed that humans actually step back into the loop for the grouping and labeling phase, right before that final accuracy assessment. It's this incredibly streamlined, fast-tracked process from raw data to a categorized map.
Let's actually break down the mechanics of how this works step by step. First, you, the user, simply specify the desired number of clusters. You just tell the software, hey, find me 20 distinct groups. Second, the algorithm goes to work. It iteratively organizes the pixels into that exact number of groups based on how spectrally similar they are. Think of the algorithm as an explorer dropped into a pitch-black room, sorting a bunch of objects just by how they feel. Puts all the smooth things in one pile and all the rough things in another. Finally, in step 3, the analyst essentially turns on the light. They look at those piles, the clusters, and manually assign meaningful, real-world labels to them.
Now, to pull off this sorting in the dark trick, the software relies on some pretty heavy-hitting math. The most common algorithms you'll run into are K-Means, ISODATA, fuzzy C-Means, and adaptive resonance. But really, K-Means and ISODATA, those are your daily workhorses. They calculate initial class means and then iteratively cluster the pixels using minimum distance techniques. With every single iteration, they recalculate and refine until all those millions of pixels are neatly organized into their spectral groups.
Moving on to Section 2, the algorithm's superpowers, and why analysts lean so heavily on this kind of automation.
So why do analysts actually love this approach instead of just spending weeks doing manual setup? Well, the perks are massive. First off, and this is huge, zero training data is required. It's highly accessible because it completely bypasses the need for you to go out and manually collect ground truth data or draw training polygons. Number 2, it reveals hidden patterns. It absolutely excels at identifying spectral classes that might not correspond to obvious land cover types or stuff that's completely invisible to the human eye. And number 3, it's incredibly fast. It allows the software to convert raw image data into structured clusters with just amazing efficiency for rapid assessments.
And this brilliantly illustrates that whole hidden pattern superpower. Imagine you're looking at a satellite image of a vast desert. To you or me, it's just sand, right? It just looks like a giant, uniform patch of bare soil. But the unsupervised algorithm, because it's looking at pure spectral data across multiple invisible bands, it easily differentiates entirely different soil mineralogies. It groups them perfectly, exposing geological structures that a human analyst would completely miss if they were just eyeballing it. All right, Section 3, Real-World Applications. Let's put this tech to work. We've covered the theory, but where is this actually being used out in the wild? Well, it's a total game changer for a few specific tasks. It's the go-to method for exploring unfamiliar terrain where ground truth data or prior knowledge are completely absent, exactly like our 50,000 square kilometer Southeast Asia scenario.
It's also perfect for preliminary landscape assessments. Analysts will run an unsupervised clustering just to get a quick feel for an area before they sink thousands of dollars into field surveys. And it's huge in automated agricultural monitoring too. For instance, researchers in Hazes City actually use these exact algorithms to successfully extract and map out the distribution of winter wheat across the entire region.
Which brings us to Section 4, the labeling problem. Because yep, this unsupervised tech definitely has an Achilles heel. As amazing as all this automation sounds, there's a catch. And there's this great quote from the remote sensing community that just hits the nail on the head. Unsupervised classification pushes the expert knowledge requirement to the end of the process instead of the beginning. The machine is blindingly fast at sorting the puzzle pieces by color and shape, but it has absolutely no idea what the final picture is supposed to be. It inherently suffers from the labeling problem. You still absolutely need a human expert at the very end to manually examine and assign a meaningful land cover label to every single cluster.
So the crucial point here is this massive fundamental disconnect. Because the algorithm is strictly grouping pixels by spectral data, the resulting clusters very rarely match neat, real-world human categories. The machine just sees groups of identical reflectance values, but the human sees a continuous ecosystem. And this clash between pure spectral reality and human semantics creates major headaches during that final labeling phase.
Let me give you a really relatable example of how this actually plays out. It's a frustrating little thing called splitting. The unsupervised algorithm scans a wooded area and decides, okay, I'm making two completely separate clusters here. Why? Because the sunlit tops of the trees have a totally different spectral signature than the dark, shaded areas between the branches, so the machine splits them perfectly. But a human looks at that exact same area and just sees one unified class, a forest. So now you, the analyst, have to go in and manually merge those two clusters back together. And then, of course, you've got the exact opposite problem, merging. This is when two completely different physical things happen to look identical spectrally. The algorithm might look at deep, dark lake water and then the dark radar shadow cast by a mountain. And it goes, yep, these are exactly the same thing, and merges them into a single cluster. As a human, you obviously know a lake and a mountain shadow are two entirely separate features, but the machine has confidently lumped them together, creating this massive map error that is honestly incredibly difficult to untangle.
Oh, and there's one more headache we gotta mention. The reset flaw. Unsupervised classification models are incredibly rigid. Let's say you introduce some new image data later on, or add new samples. While you can't just casually update the model, the algorithm has to completely reevaluate the entire spectral landscape, which means the whole classification process generally has to be repeated from scratch.
But don't worry, there is a fix. Section 5, the hybrid solution, getting the best of both worlds. Let's actually see how this builds out in the real world. If unsupervised is fast but kinda dumb about context, and supervised is smart but agonizingly slow, how did our analysts from earlier actually map those 50,000 square kilometers? Well, they teamed up. In practice, analysts almost never use unsupervised classification as the final step. Instead, it's this perfect exploratory first stage in a hybrid workflow. Step 1, you run a quick unsupervised classification with a generous number of clusters, say 20 or 30. Step 2, you use that to reveal the natural spectral structure of the area. It highlights exactly where the clear boundaries are and where the messy, ambiguous zones lie. Then, step 3, armed with that exploratory map, you strategically pinpoint those areas of ambiguity and collect training samples only where you actually need them. This creates a highly accurate supervised final map. It's machine efficiency perfectly guiding human intelligence. Unsupervised classification is just this incredible tool. It lets us rapidly decipher the raw, chaotic data of our planet, finding patterns we literally can't even see. But at the end of the day, it still heavily relies on us to tell it what those patterns actually mean. So I want to leave you with this thought. If machines can see these hidden spectral realities, but fundamentally rely on human semantics to make them useful, will true AI ever be able to map our world completely without us? Thanks so much for watching this explainer, and keep exploring.